Let's look at the next kind of nucleophile, also involving a C negative. So this is the cyanide anion. Now we've mentioned before that the cyanide anion is actually a pretty good nucleophile. It's a good nucleophile because we have a negative charge. Secondly, we have a negative charge on an atom, carbon, that has a really low electronegativity. And so therefore we would expect this particular anion to be a very good nucleophile, and it is. The problem is, it's also a pretty good leaving group. So I've indicated this first step with equilibrium arrows to suggest that, yes, our nucleophile indeed can attack at our carbonyl and become attached and form this intermediate, but it can also decompose fairly readily. So here's the thing. Generally, we do this reaction in the presence of an excess aqueous sodium cyanide. And we can't really isolate this intermediate because as soon as you isolate it separately, because there is no cyanide present in solution, the reverse reaction will be favored. We therefore need to do the aqueous workup in the presence of the aqueous sodium cyanide. Therefore, we need to add acid directly to this reaction mixture. We have to be very careful at this stage because in adding acid, we will form hydrocyanic acid, which is an incredibly dangerous acid. It can be fatal if we get exposed to this acid. So the idea is that we'll add HCl very slowly at the stage of the aqueous workup. Thereby, any of the acid that we do add will hopefully be picked up initially by the alkoxide, that being the stronger base. And so we'll accomplish the aqueous workup without generating the hydrocyanic acid. So typically you'll see the conditions looking something like this. So you'll have your cyanide, and then you'll see slow addition of HCl. I'm going to ask you to try to also show these conditions when you need to show the reaction conditions. So it's not the typical step 1 and then step 2 as the aqueous workup. That said, when we show the mechanism, it's going to look essentially very similar to the other mechanisms that we've seen. So for instance, now that I've formed this intermediate in the first step, we pick up a proton and we form this product. This product is also known as a cyanohydrin. Now this class of reactions is a little different than the other ones that we've seen from the perspective that it's reversible. And again, that's highlighted with these equilibrium arrows. It's particularly reversible in the presence of base, and we'll take a look at that in a minute. But first I'd like to run through the reaction again with you. So in this example, we start with a ketone as part of a cyclohexane ring. And here you can see those conditions again. Now I've written sodium cyanide. I'm okay if actually you just write the cyanide anion. And then you see here HCl slow addition. I don't write step 1 and then step 2. In terms of the mechanism, we can start directly with our cyanide, negative charge on the carbon, lone pair of electrons, the attack at the carbonyl carbon. And in terms of the intermediate that we will form, we will have the negatively charged oxygen, and of course we will have added our cyanide. Now because we have this extra methyl group on the left, as it turns out then, this carbon here, that is the carbon that was part of the carbonyl, is in fact chiral. And so we can actually aim for one of the particular diastereomers that will form. And I say diastereomer because actually this carbon over here is also chiral, although we don't know its orientation. So this, of course, would be one of the intermediate products. We then have so-called aqueous workup, and I'm okay if you represent it in terms of writing the mechanism as something like this. So this does imply 2 separate steps, but of course, in terms of how we actually run the reaction, we don't run it in 2 separate steps, but rather we add the HCl in situ with the cyanide there present, just enough to protonate our alkoxide. So there's one of the products. along with, of course, the methyl group on the side here. As you might imagine, the other product will be the result of the attack from the other side of the carbonyl. So let's take a look at the fact that this reaction is reversible. So as mentioned, in basic solutions, we can start from the cyanohydrin and form the corresponding ketone. The mechanism might look something like this. So we've got our hydroxide. The hydroxide is going to pull off that proton and once again form the alkoxide. The alkoxide will be involved in reforming our ketone and will lose the cyanide. Now, I want to highlight that this is unique compared to the other carbon-negative nucleophiles that we've seen, in that this cyanide, although it is a good nucleophile, it's actually a pretty good leaving group. So again, this is why this reaction is reversible. To help you understand why it's a reasonable leaving group, let's take a look at the various other nucleophiles that we've been looking at. And to look at them, it's helpful to consider their conjugate acid and think of them as being the conjugate base. So for a typical alkane with a pK of 50, then we have this CH3, CH2, negative. And while that's not exactly the nucleophile that we're using, this is representative of effectively what the Grignard is, or what our organolithium type of compound is. And as you know, this is highly reactive, highly unstable, and in no way would serve as a leaving group. Correspondingly, we have the conjugate base of our ethyne. So there it is there. Again, although the ethyne is relatively acidic compared to an alkane, this is still a pretty reactive base that we've just formed, this conjugate base. So I just want to make the comment that both of these are quite reactive, very reactive, and very poor leaving groups. As such, the addition of a carbon chain through a Grignard or the organolithium type of compound, or the addition through alkyne type of compounds, these are not reversible reactions.
By contrast, you can see that hydrocyanic acid is relatively a stronger acid, and its corresponding conjugate base is relatively stabilized.
Although it's a good nucleophile, it's not a very strong base, and therefore it actually makes a reasonable leaving group, or I mentioned at the top there, a good leaving group. As a final point then, what we've been doing so far in looking at carbon-negative nucleophiles is many of them are what we refer to as irreversible nucleophiles. So this is summarized on the next slide. So many nucleophiles are also strong bases, and the typical examples would be, for instance, our Grignard reagents. And I'll use as an example a 2-carbon chain with this bromine. Okay, so that's our Grignard reagent. That would be a very strong nucleophile, but also strong base. And of course, the conjugate base would be a very poor leaving group. We also have, of course, our organolithium type compounds. We have our alkyne type of nucleophile. And then not to forget all the hydride donors that we've been looking at. So for instance, the lithium aluminum hydride. I'm just going to draw the aluminum hydride here. And then the sodium borohydride. All of these are considered to be strong nucleophiles, correspondingly with strong bases, and essentially the addition of these things is irreversible. So we've got that first step, we form the intermediate, and then we have the aqueous workup. By contrast, the example that we've just seen involves the cyanide, and there are not many examples, and certainly not many examples that we need to worry about. So the cyanide is added, and then of course the subsequent step is the aqueous workup. But understand that we're going to imagine these reactions being as equilibrium steps. So of course the reverse process is also possible, and the loss of what was the nucleophile. So just keep these two things in mind. For the most part, the H negative nucleophiles, the C negative nucleophiles, are going to represent irreversible nucleophiles. The cyanide is a reversible one, and this is actually foreshadowing some other nucleophiles that we're going to look at that will involve water and alcohols. And we'll see that these nucleophiles are also reversible because they represent weak nucleophiles, weak bases, and we'll have to take extra steps to actually get them to react.